Welcome to part 2 in the Basic Energy Analysis series, the Baseline Model. In part 1, we saw that the pattern of energy use depends on the type of equipment connected to the metered service. We've seen that the pattern is sensitive to the time period and to the weather over that period. But those are not necessarily the only factors. Any energy specialist will tell you that consumption is also influenced by changes in independent variables related to the way the facility is used. We're talking here about variables that have nothing to do with weather. For example, as production increases at a steel mill, energy use will also increase no matter what the weather's doing. Energy use at a restaurant increases with the number of meals served, and more electricity is used when a hotel is fully occupied than when it has a lot of vacant suites. While all this is certainly true, we're going to concentrate on weather and leave the discussion of other independent variables for another video. Experience shows that in most commercial, institutional, and residential buildings, weather is the dominant variable and often the only significant one. Year-over-year weather variation can easily change heating or cooling requirements by 20 or 30%. So how are we going to reliably assess past energy performance? If we're going to figure out how well we did last year, we can't just compare against the year before. The effect of weather on the heating and cooling consumption is simply too strong. Of course, we could estimate the weather effect, but in the end, estimating always leaves questions and uncertainty. Estimation is not a good way to manage a major expense, especially when reliable software is available to handle the number crunching for us. The solution is to create mathematical models, or formulas, to describe how the metered consumption reacts to weather. When we have a model, we can plug the weather for any particular period into it to tell us how much we should have expected to consume. Industry standard practices for creating these models have become established over the past 15 years. The underlying math is not especially complex. It involves individually calculating the pieces of consumption and then adding them together. However, energy experts and statisticians have taken years to agree on the exact methods. The rest of this video will explain the important basics without getting bogged down in the precise details. In building up a model, the first part we'll look at is the base load. Base load energy use is consistent throughout the year. For any given period, the consumption is tied to the length of that period. By convention, we will use number of days as the unit of time, so the formula for base load consumption would be number of days times the daily consumption. Mathematically, we show this as Q equals Tx, where Q is the consumption for the period, T is the daily consumption, and X is the number of days. T is a constant which will be different for every metered service. It will be much larger for an office building, for example, than for a single-family house. The formula works for any time period. It doesn't matter if it's 10 days, 30 days, or the whole year. One calculation can tell you what the baseload consumption should have been for all of last year. 12 calculations can tell you what the baseload consumption should have been for each of the electrical bills during the year. Now let's add the heating component. The second term in the model is the product of a heating constant, H, and the heating load, Y, during the meter reading period. Like the daily baseload consumption, T, the value of H depends on the size of the service. It also depends on what kind of heating equipment is connected. As we've already seen, if there is no heating equipment connected, the service would not be heating sensitive and the value of H would be 0. Y is derived from the local temperature conditions over the period. You may be wondering at this point where that number comes from, and it's an important question, but we're going to leave that detail for now and return to it in a later video. The last consumption piece is the cooling component. It is handled in a very similar way to the heating. The term CZ consists of a cooling constant C for the particular metered service multiplied by the cooling load Z. The model for any utility meter where consumption depends on time and weather will be in this standard form. If you are using energy analysis software, you may not ever see it, but this is what the inner plumbing of the software should be using. Looking at the modeling process another way, we can think of it as two information packages. The constants T, H, and C are properties of the metered service. They define the model for consumption at that meter. The variables X, Y, and Z are values taken from the reading period. They are the inputs to the model. Combining both information packages, the model defining the metered service, and the conditions during the metered period, we can calculate Q, the expected consumption over the metered period. The next obvious question is, how are these models created? Where do the constants T, H, and C come from? They are calculated using a statistical process called multivariate linear regression. You feed some historical meter readings into software along with the corresponding outdoor temperature conditions, and it produces the three constants for you. The linear regression software finds the formula that most closely matches the meter readings you have fed in. Suppose your organization has decreed 2009 as your energy base year. You want to measure future energy performance against 2009, correcting for weather differences. To do that, you need to create a baseline model. First, you would feed in the 12 metered consumption values and the reading dates from 2009. The software would then pull in the local weather data. The processor would process the two parts together to calculate the values for T, H, and C. The model is the equation that most closely matches the inputs. This is your baseline model expressing consumption in 2009 as a function of the weather in 2009. It is important to keep in mind that the baseline model is just expressing a mathematical relationship. It is an equation created from the information that is put into it. This particular model is based on 12 meter readings over a single base year, but it could be based on half of one year and half of the next year, or it could have been based on more or fewer than 1 year of readings. That means that if you are missing 1 or 2 readings during your preferred baseline period, you can still create a model from the readings that you do have. That concludes this installment in our series. Thank you for watching. Please join me for Part 3, Energy Performance Tracking.